Okay, so one of the more valuable uses of resonance structures is to answer this question: which is more reactive? And that's going to be something that's not necessarily going to be obvious when you're looking at the original Lewis structure, and so then resonance structures can give you a hint at it. So for example, if you have a molecule like this, an ester, a generic ester, I'm not specifying what anything is, and I ask you which one of the two oxygens is more likely to react with this H+, which one of them is more likely to be a better base and can react with this acid, then the way you should go about evaluating that question is to say, well, okay, I've got lone pairs on each one, so I could imagine reacting with the H+, and then you start thinking about, all right, well, certain atoms are more basic than others, and so on and so forth. That's the way you'd approach this. But fundamentally, what we're talking about here is two oxygens, so they're the same, and they each have two lone pairs, so that's the same. So which one is going to react first? Well, you could just throw up your hands and say, well, it could be 50-50, but that's not actually true. Instead, what you want to do is you want to think about resonance structures. Now, there's two ways you could do this. One is to draw resonance structures at the outset with the structure as drawn, or you could imagine drawing the dotted lines, because I'm not actually doing this reaction yet, I'm just imagining doing this reaction. So the curved lines, what I could do is either do the orange reaction in order to lead to that, or I could do the pink in order to lead to that. Which one is going to win? So let's do it both ways just for fun. So let's imagine first that I have reacted according to this pathway. So the result is going to be that I'm going to put a H on this oxygen down here, which now leads to a plus on this oxygen. Why? Because it has three things bound and it has a single lone pair. And so an oxygen with three things bound in a lone pair is going to be plus. Okay, so is that good? Well, not great, not at the moment. Now, what happens if instead I react with this top guy? Which one is going to be better? So let's just imagine drawing that reaction. So now what I have is I have drawn such that I have a H on top, and this also is going to be plus, and again, for the same reason, it has a lone pair, it has three things bound. Meanwhile, this oxygen down below now has two lone pairs on it. Okay, so which one looks better to you? Well, at this point, they probably look about the same, but now I start thinking about resonance. This plus right here on this oxygen exists because this oxygen would like to have two lone pairs and two bonds. Can we achieve that? Yes, we can. Well, I can go ahead and take that double bond and make it into a lone pair. And if I do so, I will end up with a new resonance structure, one that I don't necessarily love because I'm putting a plus on the carbon, but which does at least solve the immediate problem of having a plus on the oxygen. So I can go ahead and draw this resonance structure, and it's not a particularly good resonance structure. Again, we don't like to violate the octet rule, but it does create another place where the plus can be. The plus is initially on this oxygen, but by doing this resonance form, I can put the plus right there. Or a slightly better way of describing it is this is the better of the two resonance structures, but the fact that this resonance structure exists suggests that there's more delta plus at this position than you think there is. There's more delta plus on that carbon than you would assume based looking only at this structure. In other words, the weighted average of these two is going to be slanted toward the orange, but it's going to include some of this. In other words, that area right there is more delta plus than you think. Can I play a similar game with this red one? Well, unfortunately, no. Look at these bonds. This oxygen only has single bonds to it, and it has four things bound to it. Can you push more electrons onto it? No, you can't. It's locked. Are there any resonance forms for this red one? No, there aren't. This is it. That's all you get. So which of the two pathways is better? Well, actually, using the orange oxygen, the oxygen on top, the oxygen of the carbonyl, to do the attack in the first place, leads to a situation where you can stabilize the plus that results by resonance. So this one over here wins. The oxygen on top is more basic than the oxygen down below. And the way I did this, the way I'm trying to convince you of this, is by drawing first the resonance structures of the products. But I could alternatively look at the original structure and contemplate doing resonance on the original structure in order to figure it out.
It is only now, as I am editing this video, that I regret my decision while filming to only draw two resonance structures and put it within the circle. There is in fact a third resonance structure. I have drawn the best and the third best, and there's a first/second best, sort of tied with the first, that also exists. And if you go to the end of this video, you will see that. I will diagram it out.
So which other resonance forms exist for this initial structure? Well, let's try just simply taking a pair of electrons, one of the bonding pairs of electrons, and sliding it up onto that oxygen and leaving behind the carbon unattacked with an unfilled octet. So does this new and improved resonance structure help us understand what's going on there? Not necessarily, not at first. This structure is, of course, vastly more stable than this one. The weighted average is going to look more like this blue structure and less like this one. On the other hand, what this does suggest is that there's more delta plus on this carbon than you think, and there's more minus on this oxygen than you think. So here, everything looks neutral and happy. This structure is telling you there's more plus on this carbon, more minus on this oxygen than you might otherwise think. Having said that, it doesn't really necessarily allow us to compare the two oxygens all that well, although it is giving you a hint as to what we figured out over here. If there's more minus on this oxygen than you think, and this oxygen is relatively neutral, then that suggests that the orange structure, the orange attack on the H, is going to be more likely than the pink one. But let's keep going. Let's assume, for the sake of argument now, that I would like to improve this resonance structure further. I will now take a curved arrow from this oxygen, make a double bond there, and what that will do is now improve things by having one more resonance structure that exists. So in other words, what I'm going to do from here is simply draw a double bond to the oxygen that's on the bottom right, which now puts the plus on the oxygen itself, and now we have the minus on the oxygen up top. And we have one lone pair down there. And again, all three of these structures are resonance structures of each other. And by the way, if I would like to move from this structure back to the original up there, the way I would do it is I would simply take this lone pair and push it down to create a double bond, which would then cause the double bond to kick and become a lone pair on this oxygen. And that takes me back to the original. Okay, so which of these three resonance structures is the best? The original one, no question about it, and it's substantially the best. It's vastly better than the others, so the structure of the compound is truly given by that more than anything else. But the reactivity of this is going to be given not by the best resonance structures, but by instead one of the minor resonance structures. And in particular, this minor resonance structure tells you which one of the oxygens has more electron density on it. In other words, this oxygen has a minus on it. It has more electron density than you think. This oxygen in this resonance structure has a plus on it. It has less electron density than you think. So when we were looking at this original structure, we were saying, oh, it's two oxygens, they're basically the same. Actually, they're not. The oxygen of the carbonyl is more minus than you think. The oxygen, the other one, the singly bound one, is more plus than you think. So which one is more likely to react with an H+? Well, the one that has more minus on it. So you can either figure out which one is more reactive with an external plus by looking at the original resonance structures and trying to figure out where there's more electron density, which is what I did here. Or you can draw the two products that would result and try to figure out which one is better, which is another way of answering the same question. But the core idea is, if you looked at this structure originally, you couldn't tell which one is more minus, more able to react with a plus. But after you examine some resonance structures, then you have a pretty clear idea. This oxygen, more minus than you think. This oxygen, more plus. Therefore, they will react that way. And if there is a single thing to keep in mind for why you would do resonance structures in the first place, it's this. In the end, the best reason to do resonance structures is because the structure of the molecule you're looking at is almost always going to be given by the best single resonance structure you have. That's going to be the one that's closest to the structure, unless you have two even structures, in which case the reality is going to be halfway in between. However, assuming you have unbalanced resonance structures, then the reactivity of the molecule is going to be given by one of those minor ones. So in other words, what does the molecule look like? It looks like the blue one. How does it react? Well, it reacts more like this, a relatively minor resonance contributor, but one that explains where the electron density is. If you have a completely neutral structure, then drawing some of the more charged ones will tell you where the electron density is in the molecule.
All I've done so far is to reproduce the work that was already on the light board. I have the initial structure, the problem, with the ester attacking the H+, specifically the lone pair of the carbonyl oxygen doing the attack, and that leads to this protonated carbonyl structure in orange, where the oxygen of the carbonyl has now picked up the new H, and it has become positive. Then, what I had drawn on the board was that the double bond becomes a lone pair as drawn. So the oxygen of the carbonyl was positive because it had 3 bonds in a single lone pair. The double bond is now becoming a second lone pair, which will will render that oxygen neutral. In the meantime, though, the electrons are coming from this carbon of the carbonyl, so the carbonyl ends up positive because it lacks for a full octet. That lacking for a full octet is why this is not a particularly good resonance structure. It does share some of the electron density problems, so the oxygen now isn't the only thing that's plus. Now the carbonyl has some of the plus. But of the two resonance structures, the orange one is better because everything has a full octet, even though the oxygen, being the electronegative atom, does not want to be plus. So here, the problem is that this carbon lacks an octet, and that's why this is a relatively poor resonance structure. And so the resonance structure that I had failed to draw originally and should now draw is one where this nearby oxygen becomes involved and donates its electron density to create a double bond. That will then lead to another resonance structure, one that is better than the green. All I've done so far is reproduce the portions of the molecule that have not yet changed, and so what I now need to do is include the part that has changed. In other words, this now has a double bond between the oxygen and the carbon, and that creates the positive charge on the oxygen. So we now have 3 resonance forms. Of course, if you like to interconvert the red into the orange, what needs to happen to accomplish that is this lone pair kicks down and becomes a double bond, and this double bond will now become a lone pair on the oxygen to the bottom right. And that's how you interconvert between the structures. So the structures are then essentially tied in which one is best. To a first approximation, the structure in orange and the structure in red are both substantially better than the structure in green, and the structure in green is substantially worse because it lacks for a full octet on the carbon. So the structure in orange and the structure in red both have full octets for everything, and they are essentially tied. There really is no difference between which oxygen prefers to have the plus on it, and formally it is the same. The resonance hybrid describing this molecule probably looks something like the structure down here in the lower left-hand corner, where the two oxygens bear the vast bulk of the charge between them, maybe 90% of the charge, split evenly, and that's because the orange structure and the red structure are vastly better, vastly more stable than the green one. The green one lacks for an octet at the carbon. Having said that, the overall picture is clearly going to have some charge on the oxygen, some charge on the other oxygen, and some charge on the carbon of the carbonyl as well. And so if there's 100% charge to be distributed, this is totally a guess, but I would distribute it evenly between the two oxygens with a much smaller portion on this carbon right here. Having said that, if this was going to react in some way with an incoming nucleophile, there's really only 2 possibilities. One is you pull this hydrogen off, which returns you back to the original structure, and the second is you attack the carbon of the carbonyl. So even though the charge is currently borne largely by the oxygen formally, in practice where you're going to attack is the carbon of the carbonyl.